In this lesson, we're going to learn a very useful technique called convolution. Let's see how this works. Let's take a grayscale image. For simplicity, let's assume that this grayscale image was 6 pixels in height and 6 pixels in width. A computer interprets this image as a two-dimensional array of pixels. Since this image is grayscale, every pixel will have a value between 0 and 255. 0 being black and 255 corresponding to white. Here we see an example of the pixel values for this 6 by 6 pixel image. As you know, when we process this image in our neural network, the pixel values will be normalized to a value between 0 and 1. But let's keep the original pixel value to keep our explanation simple. The idea of a convolutional layer is to create another grid of numbers called a kernel or filter, which can be seen here in this 3 by 3 matrix. Then we can scan this kernel across the image. Now, here we see the image pixel values and the kernel. The image size is 6 by 6 and the kernel size is 3 by 3. A convolutional layer applies the kernel over the regions of the input image. For example, let's say we'd like to begin by performing a kernel convolution on this pixel value of 25. The first step is to center our kernel over the pixel that we want. In this case, we can see it here in green. So now, we're only going to look at the pixels within this 3 by 3 grid that is centered on the green pixel. The grid is 3 by 3 because this is the size of our kernel. So now, we take each corresponding image and kernel value, multiply them together, and then we sum up the whole thing and assign it to the green pixel in the convoluted image. Let's see how this works step by step. So the first image pixel value in this grid is 2. So we multiply that by the corresponding kernel value, which is 1 in this case. So 2 multiplied by 1 equals 2. We do the same with the second image pixel value in the grid. We can see that it has a value of 5. So we multiply that by the corresponding kernel value, which is 2 in this case. So 5 multiplied by 2 equals 10. Now we do the same with the third image pixel value in the grid. We can see that it has a value of 4. So we multiply that by the corresponding kernel value, which is 1 in this case. So 4 multiplied by 1 equals 4. We do this for all the remaining pixel values inside our blue 3 by 3 grid. Once we have the result of all these operations, we sum all the numbers to get a total value of 198. So 198 will be the corresponding value in our new convoluted image. And now we can do the same with all the other pixels in our image. However, what happens to the pixels on the edges? For example, what will be the corresponding value of this pixel? We can see that when we center our kernel around this pixel, the grid lies outside the image. So what should we do in this case? There are a couple of options. One is not to use this pixel in the convolution, so we just ignore them and pretend they don't exist. Sometimes this is done, but the downside is that you will lose information about the image because the convoluted image will become much smaller than the original image. A more common option is to do something called zero padding. In this case, we add pixels with 0 around the original image, as we can see here. Now that we have filled the missing pixel values in our grid, we can calculate the kernel convolution just as we did before. And in this case, we get a value of 22. Similarly, we can add zero padding to the entire image, like we see here, in order to calculate the kernel convolution of the entire image without losing information. So a kernel convolution is just this process of applying the kernel or filter across different areas of the input image. And similarly to a dense layer, we'll see that convolutions are another type of Keras layer we will use. Now, let's take a look at another essential concept we need to understand convolutional neural networks: max pooling.